Okay, so now we will start to talk about introductory example. So for the hypothesis test of 3.1, we can easily find the Neyman-Pearson test. Assume that we require PFA equal to 10 to the minus 3. Then from 3.3, we decide H1 if this. What is 3.3? We have a likelihood ratio. So you assume that L is the P of X conditional H1 over P of X conditional H0 larger than gamma. Then uh, assume that we require this label of probability of false alarm. Then our decision is we do we do formulation for this, and it gives us this. How come? Try to imagine this. Conditional H1, you have a Gaussian distribution. Conditional H0, you have another Gaussian distribution. So, well, in fact, you have two Gaussian distributions, right? Two Gaussian distributions. One is zero mean, and the other is with mean 1, mean equal to 1. So you have two distributions. So you set a ratio on that, which is to just follow this. And then, as you know, this cancel out. This cancel out. Exponent, if you have something exponent, then they divide with respect to each other. The outcome is just the minus of the exponent. So it's the exponent of this minus this. So you get this. Finally, you get this. This is just because you see this and this cancels out, right? So you get something very simple. In fact, you can just put some of the uh, unnecessary parameters are cancelled out or they are simplified. Then at the end, you get this. You get this. Get this. Okay, so now let's continue to page 66. So at this point, we could determine gamma from the false alarm constraint. The probability of false alarm is equal to probability of this conditional H0, right? Which is right, which is the probability of this larger than a threshold gamma, and that conditional H0 equal to the constraint that is preset. That is preset. Then we need to simplify this whole thing. We need to simplify this whole thing. So if we just take logarithm of both sides, this is because logarithm is a monotonically increasing function. So if you just take logarithm, then the whole thing is simple. The whole thing is simple. Uh, so alternatively, since gamma is larger than 0, we will let gamma equal to exponent of x, exponent of beta. The reason for doing that is to as a change of variable，变数变换，这只是变数变换而已。Okay, so that we decide h1 if this equation sustains. Notice that those are things to be decided. After it's decided, what we have will be the realization, which is x0. When we get x0, then we plug it into here and we make decisions. Alright, so if it's like this, and then you have something like this, because you take the exponent out, you take the log, right? Take the natural log, then exponent will disappear. This will disappear. You get something like this, and you get something like this. Then you will let this gamma prime equal to Ln gamma plus 1 over 2, so on and so forth. So you decide H1 if this is larger than gamma prime. To explicitly find gamma prime or equivalent gamma, because notice that gamma and gamma and gamma prime, they are uh, uniquely determined by each other. If you decide gamma, you decide gamma prime. You decide gamma prime, you decide gamma. So they are uniquely defined with respect to each other. So it's not an issue to find gamma or gamma prime. Whichever you find, you get the other. So we use a PFA constraint. PFA equal to PR x0 larger than gamma prime. Conditional h0 equal to this. Of course, then conditional h0, this distribution is known, right? This distribution is the Gaussian distribution with zero mean. And then it will be integrated from gamma prime to infinity. So it has to be like this. And then how should we decide gamma prime under which it will be equal to 10 to the minus 3? This is again a numerical issue. And then of course then at the end we decide that gamma prime is equal to 3. Okay. The NP test is to decide H1 if x of 0 is larger than 3. That's a detector of the previous example. Is indeed minima in the NP sense, in that it maximizes PD. As before, we find PD as follows. Right? We find gamma to satisfy this constraint. Now we come back to find PD. PD is to find x larger than 3 conditional H1. So it will be 3 to infinity, and then something like this, and then dt. This is a Gaussian distribution with 1 as the mean. It's equal to 0.023. Alright. Notice that the detection performance is poor because the PD is very small. We will usually expect PD to be something large, right? For example, 0.9, 0.8, but now we see we have a very small PD. The reason is that we put a very strict requirement on PFA. Our PFA is very small. As a result, the PD is very small. Although we have satisfied our false alarm, we will only detect the signal a small fraction of the time. To improve the detection performance, we can increase PFA. Okay, that is usually a trade-off. For example, if PFA is 0.5, then we do it again. The threshold is found to be like this, as gamma prime equal to 0. Right? That is found from this equation. Then we'll calculate PD again. Okay, it follows the same rule as here. Okay, it follows the same rule. Then we have a PD again here. Then we calculate it if it goes from 0 to infinity, so on and so forth. And then we go to the next page, 67. It's a Q function of 0 minus 1 over 1, which is equal to Q of minus 1, which is equal to 1 minus Q of 1.84. Okay, Q 0.84. So you see, we have better PD, better PD. Then the reason is that we are accepting more PFA. Previously, we like it to have 10 to the minus 3. Now it's 0.5. It's 0.5. So as a result, we have 0.84. 0.84. Okay, so that's sort of a trade-off, an obvious trade-off，就是我们如果容许我们的 PFA 不好很大的话，诶，那我们的 PD 也变好了。那这个看起来，如果大家从工程的角度去想，合不合理呢？是很合理的，因为我们对 PFA 非常严格。第一个例子，看这里哦，我们对 PFA 非常严格，10的负3的 PFA 是很小的。那在这种情况之下，没办法，你的 PD 也会很小。我们接受 PFA 大一点，可以吗？如果可以的话，诶，那你的 PD 也会好很多，你的 PD 也会好很多。所以这就是一个看从工程的 trade-off 的角度来看，然后那事实上这很合理啦，因为工程上就是很多东西是 trade-off，我们不想要的特性跟想要的特性互相之间有一个 trade-off，那不会说哦，我们不想要的东西变成0，我们想要的东西变成1，那这个是一个这一种问题会变成是一种 trivial 的问题啊，就是它是一个太简单的问题，那这种问题通常很容易就被解决掉了，其实也不太需要讨论的哈。那我们会讨论的就是这种需要 trade off 的。Okay, so now let's come to the DC level in wide Gaussian noise. Now we consider a more general signal detection problem. We have a H0 equal to Wn, or with the other alternative hypothesis is H1 its sample is equal to A plus Wn. Then that A is the general value instead of just a 1 before. 先前记得吗？我们讨论的时候，我们说，诶，这里 signal 就是1，现在没有，现在的讨论是说，诶，这个 signal 是 A 是一个 general value 哦，它不是说是一个特定的 value 哦，所以我们就把这个问题更一般化了，叫做 general is a more general version of the problem. And then Wn is still the white Gaussian noise with variance sigma square. Then the previous example is just a special case when A equal to 1, right? A equal to 1 and N equal to 1 and sigma square equal to 1. Besides the A is generalized, we are taking multiple samples here. 我们有多个 sample 了，除了不是只是像先前是一个 sample. So we have multiple samples here. N equal to 0, that's small index n. Okay, small index 0, 1, all the way to minus 1. So that also corresponds to multivariate Gaussian, right? That's why we talk about multivariate Gaussian and vector version of the Gaussian. This is because on the H0, X is distributed with 0 min and sigma square I, while on the H1, its X is distributed by A with 1 and sigma square Y. Okay, so that's very different. Alright. We have a vector version now to clarify. we have a vector version now with 0 sigma square I, and then A multiplied by 1, okay, and then sigma square I. Remember that 1, 这个 capital 1是一个 column vector，所有的 element 都是一这样啊，一这样一直下去哦，哈，这个不是一个 identity 哦，这里这个 I 才是 identity，这个不是 identity，这个是一个 column vector。So we have an explanation here. The one 写起来有一点厚，比较黑的这个 one is a vector for all ones. It's a column vector, in fact, column vector. Hence, we have equivalently h0 equal to mu equal to 0, h1 equal to mu equal to a1. We'll often use this parameter test of the PDF interpretation in describing the signal detection problem. So the MP detector decides h1 if this is uh, this is what this is the previous page 63 65. We are actually calculating this 3.3. Okay, so now we come back. We just write down the formulation for a probability density function, then we get something like this and something like this. Of course, then some of the things can be simplified, right? Exponent, some of the things inside the exponent can be cancelled out because they are divisions and larger than gamma. Take the logarithm of both sides results in log n, and then log this exponent, and of course log exponent disappears. So we have this coming out, then that satisfies to this. Just to be clear about this, in this case we have multiple samples, 0 to 1 to n minus 1. So how many samples do we have? We have n samples. So as a result, you will see that n comes into the equation. And this is reasonable because imagine this, the more samples you take, the more accuracy you have, right? So if you are expecting more samples to contribute to your accuracy, then you should expect n to be in your equation. So, but of course that n is given. In this problem it's given. It's not something to be decided, it's given. So you have n inside here, a squared, sigma squared, then gamma. Then you have something like this. It's mathematically it's just simplification of this equation, then it goes here. Okay, not a big deal. It's not a big deal. Then we have 68, page 68. Then since a is larger than 0, we have finally this equation. Alright? This equation comes from just a sequence of mathematical manipulations and mathematical simplifications, and at the end of the day you get this equal to this, right? So what's been said here is this is a mathematical equation. So when you have n observations comes in, you do this equation, you compare with the threshold, then you make the decision. That's mathematically speaking. But another way to look at it is to see this as a sample mean. This is in fact a sample mean. You take the mean of the samples and you compare it to a threshold. Well, let's come back and see if that's reasonable. We do the mathematics now. You see that we are comparing a sample mean with a threshold. Without doing that, without doing that, let's take a look. You have n samples. Now you're comparing a hypothesis with the A, the other hypothesis without A. Would it be reasonable, intuitively reasonable, to just say, I take the sample mean and then compare? It seems reasonable, right? Intuitively, it's reasonable. 我是说，直觉上来讲，我们如果没有算这些数学的话，然后你遇到这样子的一个工程问题，你会怎么解决？直觉上来看，我们可能就会很直觉的说，哦，那我就 take 一个 sample mean，然后来比较一个需求就好了。因为为什么？因为一个是没有信号，一个是有信号 A 啊，对吧？所以我们就会直觉上觉得说 take sample mean。那这刚好和我们数学上导出来的结果是一致的，所以直觉上刚好跟数学的理论是符合这样子。我是想要表达这一点，让你们也可以理解。Mathematically, it's consistent with our intuition. Okay, so it has explained here. This is intuitively reasonable since x bar, which is the simple mean, may be thought of as an estimate of A. If the estimate is large and positive, then signal is probably present. 如果这个 sample 面是大的，那我们就会假设说，哦，那大概就有讯号吧，哈。工程上也是直觉上都是合理的啦，哈。如果有一些东西算出来跟我们的直觉不合，那我们就会再 double check 数学是不是有算错啦。但是有时候的确有些问题，它的数学结果跟我们直觉并不吻合，哈。但是大部分都是吻合的。Okay, so okay. So how large the estimate must be before we are willing to declare the signal is present depends on our concern that the noise only may cause a large estimate. Right? This is the probability of false alarm, right? You have a coincidence that the noises are somewhat large, and as a result, you have a large sample mean. Then you make a mistake for PFA. So to avoid that, we need to adjust gamma prime to control PFA with larger threshold values, reducing PFA. So to determine the detection performance, we must first know that the test statistic is Gaussian under each hypothesis. Test statistic. I'd like to explain a little bit about this test statistic. When you are given a problem, you need to do somewhat of summary, some kind of summary or calculation on the samples, and then you come up with the summary of the number. That is called test statistic. 就是这个是一个统计量啊，哈。当你给了一大堆 sample，你被给定一大堆 sample，比如说我给你100个 sample，那你可能会经过一些计算、运算、简化之后，你拿到一个统计量，然后你就用这个统计量来作为你做决定的基准。这个统计量我们叫做 test statistic. This is very important because you are going to see this terminology very often. If you are in communications, in signal processing, then you are going to see this from time to time. Okay, and the test statistic can be simple, can be complicated. It can be anything. Okay, but in our case, it's simple. It's just a average of the whole samples. So it's T of X. So it's Gaussian under each hypothesis. And the means and variances are like this. If it's on the H0, then of course, then X is just omega, right? Let me just say W. X is just W without signal. And you are taking the average of the noise. Then you take the expectation. You do the calculation, you get zero. You get zero. But if it's on the H1, then you have a simple sample mean as a signal, A, right? It has a A here. So you you uh you take the T of X sort of the test statistic on the H1 and you take the expectation, you get A. And then if you take the variance of T of X H0, then you are starting to take the variance of this thing. This thing is the same as this thing, okay? And then, of course, all the samples are IID, and then the variance comes in. If they are not IID, the variance does not come in. Okay, this equation sustains only if the samples are IID. So now you have this 1 over n squared, which comes in here, then sigma squared over n. Then similarly, for this statistic condition on H1, it's actually a sigma squared over n. It's the same thing, right? Where we have noted that the noise samples are uncorrelated, right? Uncorrelated. So T of X, which is I like to emphasize the test statistic, is the Gaussian distribution of zero mean with this variance on the H1, H0, or when it's on the H1, then it's A as a mean, and then this as a variance. We have then PFA equal to something like this. PFA is a test statistic larger than gamma prime. How come it's gamma prime? How come? Uh, because we have derived it here. We have derived it here, right? We say that from likelihood, it all started from likelihood ratio. Remember, this is not arbitrary mathematics. It goes from likelihood ratio, simplification, further simplification, and then step by step goes to this. So well, it's H0 is distributed this way, and it has statistic larger than gamma, then what's happened? What happened? We make an incorrect decision on H1. That's why we call it a false alarm. So then it becomes a false alarm. So now that false alarm becomes a Q function because it's Gaussian distribution, and then Q function this way. It has to be divided by a standard deviation. Right? You take the square root of the variance, you get standard deviation. And then when it's divided by standard deviation, it becomes standard Gaussian. And then when it's standard Gaussian, then we can use Q function. Q function only applies to standard Gaussian. So that's how we come up with this Q function. Okay, and then what's PD? PD is when you condition on H1, you take the statistic to be larger than gamma prime. Then that T is what? T is A as the mean and sigma squared over n as a variance. So what happened is you have to make it minus A because you recall that I have emphasized many times Q function applies to standard Gaussian. Standard Gaussian means zero mean and 1 as a variance. So you have to make gamma prime minus 1 divided by this standard deviation. Alright, so we have PD, and then PFA. Okay, so I think up to this point, let's take a break and come back later.